Morning, everybody. My name's Alex, and I'm pleased to introduce to you Team V.A.D.R, which stands for Vectored Autonomous Delivery Robot. Our team consists of 5 electrical engineering students: Christian, Anand, Gerald, Ali, and myself, and 2 computer engineering students, Tong and Joe. So Team V.A.D.R is part of SDSU's sponsored Payload Delivery Challenge this Thursday at 1 o'clock. So the Payload Delivery Challenge consists of 3 senior design teams, and each team's main task is to design an autonomous system which will deliver several payloads across a large area on campus, the music field, the field behind the music building on campus. So in the next slide, we're going to play a short video, which is a conceptual representation of our system, which is an aerial drone, navigating phase 1 of the competition. So in phase 1, each team competes individually, and their system will navigate from the start location off to the side of the field to the first target location and trigger a payload release mechanism, releasing a payload on the target. Each target is marked individually with a unique GPS coordinate, an RF beacon, and a small brightly colored plate on the ground. So after completing payload release at all 3 locations, the drone will autonomously return to the starting location, which is a requirement, and safely. So in order to score points in this part of the competition, the closer the payload is to the target location, the more points you achieve in this phase. And in the second phase of the competition, all 3 teams will be competing at the same time. And only one of the target locations is going to be broadcasting an RF beacon. So the team within 2 minutes that can deliver their payload to that location accurately and return to the starting location will win that part of the competition.
All right, as you can clearly see, for our solution, we chose a quadcopter drone here. That's suspending a payload delivery device that is powered by a simple servo to turn one bulb to fall on each target at a time. So in designing the drone, we did have to fall within some design constraints, such as it did have to be fully autonomous with return to base functionality, meaning it'll go out, do its mission, drop 3 payloads, and come back all on its own. You did have to account for other things such as GPS to even get to those targets, and the challenge itself had to be done within 2 minutes and within 25 feet of accuracy. So moving along to looking at how we have everything set up here. The Pixhawk is, as you can tell from the picture, is really the brain of the entire drone. At the top, you can see here in the green, we have the battery and the motors. And the left, we have all the inputs going into the Pixhawk, such as the GPS, the switch, and the receiver. Moving on to the right, we have the outputs such as the servo and the telemetry radio, which communicates with the ground station from the drone itself. And on the bottom here, it's not really connected, but that's the ground station which communicates to the drone the entire time.
Thank you, Gerald. I'm going to be talking about the hardware components. First of all, I want to start off with the frame and the landing gear that we picked. We actually selected this frame that comes in ready to assemble. And the landing gear was selected because it can accommodate the drop-in mechanism that we later will talk about. Next, I'm going to talk about the power system. For that, we're using an 11.1 volt 3-cell lithium battery, and that's going to support 13 to 15 minutes of flight time. We also have the power module. The power module actually is very important to the project, and it gives 11 volts to the board, and 5 volts actually from that goes to the power of the Pixhawk. This thing actually also helps us monitor the voltage. So if it drops below a certain voltage, it's going to tell the drone to go back to the starting location. Next, we have the voltage regulator, and that actually steps down the 11 volts to 5 volts to power the servo motor so we can drop the power of the mechanism. Next, we have the 3-phase motors that we use, DJI motors and ESCs. The ESCs drive each one of the phases of the motors, and they get back an EMF voltage that actually looks at the voltage and sends it to the Pixhawk, and the Pixhawk monitors that and adjusts the speed of each motor. Next, we have Tom to talk about the communication.
The telemetry unit allows the drone to communicate wirelessly to our ground station. It utilizes a 915 megahertz frequency. In addition to sending commands from our ground station to the drone, we can also receive feedback such as altitude and velocity. In the event that we do lose communication, we can configure it to either return home or complete the mission. In this particular instance, we want to complete our objective, so it's going to be flying blindly if we ever lose communication with it. Although the mission is autonomous, we did need to use an RC remote to calibrate the motors, and in the event of catastrophe, we can fly back manually. The RC remote itself sends out 8 PWM signals. The Pixhawk doesn't support PWM input signals. We had to use a PPM sum encoder, consolidate 8 of the signals into one PPM signal. Since accuracy was important in this objective, we wanted to go with a GPS module that we want to go with the best we could find. This one spec'd out to be accurate up to 0.9 meters, and upon testing, it was 0.9 meters. During the testing, we were able to lock onto 17 satellites. The more the better, but of course that changes throughout the day. During our testing, the drone in the middle, the green drone in the middle is where it's reporting. The red dot right below it is the actual location. We decided to go with the Pixhawk flight controller because of its popularity. It had a lot of libraries available. In addition, we were able to modulize many of the parts. It's running on an STM ARM Cortex processor. The modularization was important because of our design and weight constraints. We didn't want to include anything that we didn't need, and we were also able to test out different parts that were optimal for our solution. For example, we tested out 2 different GPS units, and we decided to go with the one that was more accurate. And our payload delivery system, Ali?
This is our payload delivery mechanism. At first, we used Google SketchUp to mock up the idea we had, and then we designed it using SolidWorks and 3D printed it to look like this. Also, we used a servo motor for the system. So basically, the servo is controlled by the Pixhawk as it outputs a PWM signal at each waypoint. How it works, it starts with its initial position at 800 microsecond pulse and steps 3 times with equal increments until it reaches 2200 microseconds. And at each increment, it releases the payload, as you can see there. Moving on to software with Joe.
Okay, so once the drone is completely built, we moved on to the software. And the software we use for this project is called Mission Planner. It's a powerful open source software that's compatible with the Pixhawk. And we use Mission Planner to calibrate and configure some of our components, such as the accelerometer, compass, and remote control. We also use Mission Planner to set up some flight modes. So the default flight mode is stabilized, which is manual control of the drone using the RC. And the mode we're using for the competition is called auto mode, and we set that to flight mode 6. And we also configured the remote control's gear switch to activate flight mode 6. To set up the mission, we go over to this flight plan tab, and we come down to the command list where we create some commands. The first command is takeoff. Second command is waypoint, where we enter in our GPS coordinates. And after the waypoint, we have a do set servo with a specific PWM value. And what this does is once the drone reaches the waypoint, the Pixhawk will send the servo motor this PWM value, causing the servo to turn and drop the payload. Then we have 2 other instances of the waypoint servo combo, and then finally we have return to launch. Okay, so here is a video of one of our test runs. So the first thing I'm going to do is arm it using the RC. Then I'm going to give the motors a little bit of throttle, and once the motors are spinning, I'm going to flick the switch to activate auto mode. So auto mode is activated. It's now fully autonomous, so I can set the RC down and follow it to the first waypoint. So once it reaches its first waypoint, it'll drop off the payload, and then it'll go off to the second and third one and do the same thing. And for this test, we configured the drone to cruise at a very slow speed, low altitude, so we can follow it around and see exactly what's going on and make sure everything's working. And for the competition, we're going to speed it up about 3 times the speed. And then so now it's reaching the third waypoint, just released its third payload. Now it's going to return home, hover over the launch point, slowly descend, and eventually land. And we configured the drone to descend at a very low speed so it will land softly and not break anything. Next on to
weight analysis.
And as you can imagine, we had weight constraints because we chose an aerial drone. And for the motors that we selected, it was a maximum rated weight of 1,600 grams. And we came in underweight at about 1,320, including everything on the drone, including the battery and frame and motors, which take up about 90% of the weight. And for the budget, each team was given $950 available in their budget to spend accordingly. And we came in under budget, spending about $630, with most of that being in the hardware, battery also. And we wanted to make sure we had extra room in our budget for replacement parts, such as our propellers that we had to replace, and upgrades, such as our GPS module. And here's a quick overview of some of our milestones. The first thing we had to do was choose an approach, and we chose to go with the aerial drone just for speed and accuracy, also to avoid any ground obstacles. And for the next major milestone was a mission planner simulation. We wanted to make sure we can simulate the drone carrying out a mission before we tested it with the hardware. And for the major milestone was a fully autonomous flight with payload delivery to the GPS coordinates, and we were able to achieve that, as you saw from the video, basically replicating the challenge that's going to be on May 4th at 1 p.m. And so we were able to achieve that. So with the fully autonomous flight. So yeah, we hope to see you on May 4th at 1 p.m. Thank you for your time.